Hello APC Mechanics students, in Unit 2 Newton's Laws of Motion, Class 15 Circular Motion, Part 4. Then let's start with Section 1, Conical Pendulum. The conical pendulum is an extension of the simple pendulum in which the bob, instead of moving back and forth, moves in a circle almost in a horizontal plane. The rope is of length L and makes an angle theta with the vertical. Here we suppose that the bob moves in a horizontal circle and with constant speed. What are the forces acting on the bob? We have the pull of gravity, we have the tension along the string. Now, if this is the angle theta with the vertical, then that would be also the angle theta with the vertical. And by that, let's construct the FBD of the block. We have the pull of gravity down, we have the tension making an angle theta with the horizontal. And now let's apply Newton's second law. Remember that this is a vector equation and can be projected along several directions, in particular two, which gives the birth of two linear equations. What are the external forces acting on the bob? So that should be the bob. Now let's consider the centripetal direction. This is the centripetal direction, and that would be the vertical. Now the pull of gravity has no component along the centripetal, then that would be 0. If this is the angle theta, then that would be Ft cosine theta, and that would be Ft sine theta. Now this is the first equation. Along the vertical, we would say that Ft cosine theta would be balanced by the pull of gravity, which is nothing but an extension of Newton's second law. This is the second equation. And now let's divide the first equation by the second equation. We have Ft sine theta divided by Ft cosine theta is mv square over r divided by mg. M with m cancels, the tension force cancels as well, and we have the tangent theta as v square over rg. Then in this case, the speed is given by the square root of tangent theta multiplied by rg. Then the equation for the speed of the bob of a conical pendulum is given by tangent theta as rg, and remember that no need to memorize this expression, it can be always determined from Newton's second law. And moreover, the radius of the circular path can be determined in terms of the length L of the string using trigonometry. Now this is the circular path along which the bob moves, and the radius of the circular path is given by r. It can be related to L and the angle theta. Knowing that sine theta, if you complete this triangle, now r for theta is an opposite, so sine theta would be r divided by the hypotenuse. This is the 90 degrees, then L is the hypotenuse. In this case, r is given by L multiplied by sine theta. So basically, for a conical pendulum, we are interested in two equations, that the speed is given by radical tangent theta rg, and the radius of the circular path along which the bob moves. So remember that the bob moves in a horizontal circle, is given by r is equal to L sine theta. L is the length of the string, and theta is the angle that the string makes with the vertical. Now, string in a vertical plane, a bob of mass m is attached to a string and swinging in a vertical plane. The forces acting on the bob are the pull of gravity and the tension force. We can consider different points along this vertical circle. So at the point A, what would be the forces acting on the bob? We have the pull of gravity down, the tension up, and in this case we can say that Ft minus Fg is mv square over r, knowing that the centripetal direction would be the positive direction and this is negative. Now at the point B, which is at the left, now we have the pull of gravity down, we have the tension. No need for the pull of gravity, we can directly say that the tension force is equal to mv square over r. At the point C, which is up top, we have the tension to be down as well as the pull of gravity, and that would be Fg plus Ft is mv square over r. At the point of D, which is right, we have the pull of gravity down, we have the tension to the left, and that would be the tension equals to mv square over r. Now section 3, tube of ride. So all of these are applications on circular motion. A student rides inside of a hollow cylindrical tube that pins the student to the inside wall of the tube as it spins, known as the tube of ride. Before the tube starts to spin, there is a support preventing the student from falling. After spinning and exceeding a minimum speed, this horizontal support is removed and the student remains glued to the walls. Now here we're talking about minimum speed, and this is reasonable because as this tube of rice starts to spin, we need to exceed a minimum speed in order for the student to adhere to the wall, to be glued to the wall. The aim of this section is to determine the minimum speed required for the student to remain in contact with the inner wall. What are the forces acting on the student? We have the pull of gravity down, we have the normal push. Why the normal push is to the left? Because this is the support, which is the tube, and the student is in contact with the inner tube. Then there will be a normal force exerted by the walls toward the center, and we have the friction is up. Why friction is up? Because here we suppose that the student will fall down, then friction is opposing the tendency of motion, which is down, then the friction would be up. And in this case we are talking about static friction. Why it's not kinetic friction? Although the student is moving, but there is no relative motion between the surface of the wall and the student, him or herself. And the normal push Fn, this can be done using Newton's second law. F net is ma. Now what are all the external forces acting on the student? We have the pull of gravity, the normal push, and the friction is equal to ma. Knowing that this is a vector equation, it can be projected along different directions, giving the birth of two linear equations. Along the centripetal direction, then this is the centripetal direction. Knowing that this is positive, the pull of gravity is 0, the normal force is the normal force, and the friction is 0, that would be mv square over r. Then Fn is mv square over r. Notice that we are interested in determining the minimum speed, but we have two unknowns, the minimum speed and the normal push. So the normal push can be determined by considering the vertical. In the case of the vertical, we can say that Fg equals to Ff, the force of friction. These are balance forces. Minimum speed means we are at the verge of slipping. So remember that the friction cannot be used as mu s Fn unless we are either at minimum or maximum, which means the verge of motion or slipping. Then now, because we are interested in determining the minimum speed, then the friction can be replaced by mu s multiplied by Fn, which is mu s m v square over ry, because remember that we have determined the normal push to be what? To be mv square over r. Then now we have two equations, that the pull of gravity is Ff, and Ff is mu s mv square over r. And now we can equate them. We have that mg is mu s mv square over r. M with m cancel, then v square is given by, so if we try take this to the other side, that would be 1 over mu s rg. Then v would be the square root of 1 over mu s multiplied rg. So what does this expression represent? This is the minimum speed required for the student to remain glued or adhere to the inner walls of the tube. And now for the rest of the video, we're gonna solve some exercises related to circular motion. Now exercise 1, an ant of mass m clings to the rim of a flywheel of radius r as shown above. The flywheel rotates clockwise on a horizontal shaft s with constant angular velocity omega. This is repeated, let me erase it. As the wheel rotates, the ant revolves past the stationary points 1, 2, 3, and 4. The ant can adhere means it sticks, to the wheel with a force much greater than its own weight. It will be most difficult for the ant to adhere to the wheel as it revolves past which of the 4 points. So we need to determine which point among points 1, 2, 3, and 4 would be the most difficult for the ant to adhere to the wheel, so remain stick to the wheel. Now basically, if you think about it, the most difficult point would be the point 3, but we need to utilize this at the level of the forces. And if you refer to the text, they only mention 2 forces. They mentioned the adhering force, and I will name this to be the capital force F, and the weight, which is basically the pull of gravity. They didn't mention anything about the normal push, so let's ignore it for this exercise. Now, in order to do so, we need to utilize the different forces, different direction of the forces acting on each of the following 4 points, and we need to set up the FBD in order to write perfectly the equation related to Newton's second law. Then let me start by the first point. At the first point, what do we have? We have First of all, the adhering force would be always pointing toward the center. At the point 1, we would have the pull of gravity down, so that would be Fg, and we have the adhering force which is also down. So if we need to set up this equation, that would be F plus Fg equals mv square over r, which means that the adhering force is given by mv square over r minus the pull of gravity, which is basically mg. Then let me write down for the first point, which is the point 1, we have that the adhering force is given by mv square over r minus mg. Now for the second point, what do we have? We have the pull of gravity down, and we have the adhering forces pointing toward the center, so we can say that the adhering force is equal just to mv square over r, because both of them are along the centripetal direction. Only the adhering force, the pull of gravity, is acting down, so F would be equal to mv square over r. Now for the third point, we have the pull of gravity to be down, we have the adhering force to be up, so that would be F minus Fg equals to mv square over r. Taking into consideration that the positive direction is always toward the center, then the adhering force is given by mv square over r plus mg. If we take this to the other side, then the adhering force is given by F is equal to mv square over r plus mg. For the fourth point, which is the point on the left, the pull of gravity is down and the adhering force is to the right, so toward the center, that would be F equals to mv square over r. So now if you take a look at all of these four expressions of F, the greatest value would be the third one. And now let's give an interpretation for this one. So the adhering force must be maximum at the third point, which means at the third point it would be the most difficult for the ant to adhere to the wheel, because it requires the maximum amount of adhering force compared to all of these four. Then C would be the correct choice. Now exercise 2, okay, we have the same given. An ant of mass m clings to the rim of a flywheel of radius r as shown above. The flywheel rotates clockwise on a horizontal shaft S with constant angular velocity omega. This is repeated. As the wheel rotates, the ant revolves past the stationary points 1, 2, 3, and 4. The ant can adhere to the wheel with a force much greater than its own weight. What is the magnitude of the minimum adhesion force necessary for the ant to stay on the flywheel at the point 3? Now we're talking at the point 3. Already in the previous exercise, we have determined the expression of the force F, which is given by mv square over r plus mg. Then the force F at the point 3 is given by mv square over r plus mg. Now notice that here we don't have v, we have omega, but v can be transformed into omega using the following relation, and that would be m r omega square divided by r plus mg, and that would be m r square with r, we would have r omega square plus mg. And in this case, the correct expression, we're using the small radius r not capital radius, and the correct expression would be E. Exercise 3. A car is moving along a road curve over a hill from point A to point B. At point A, the hill has a radius r and the car has a speed v and a tangential acceleration a. So basically at point A, we have two accelerations. We have the tangential acceleration to be a, and we have the centripetal acceleration, which is given by v squared divided by r. Now at point B, the hill has a radius r over 2 and the car has a constant speed v over radical 2. Now because the speed is constant, the tangential acceleration is 0, and the centripetal acceleration would be given by v over radical 2 to the power of 2 divided by r over 2, and that would be v square over 2 divided by r over 2, and that would be v square over r. Although at point B the speed is different and the radius of curvature is different, however, if you do the factor of change perfectly as I did, you would have that the value of the centripetal acceleration is the same as the point A. Now what's the difference then between points A and point B? Both have the same centripetal acceleration, but at the point A the car has an additional acceleration given by the tangential acceleration, which is A. Then the magnitude of the total acceleration at the point A is greater than at the point B, and in this case we can say, okay, which of the following statements about the acceleration of the car at the 2 points is correct? The magnitude of the acceleration is greatest at point A because the tangential acceleration at the point B is 0, then that's the correct choice. And you can check all the other statements and do an argumentation that they are wrong. Now exercise 4, blocks A and B of masses 1 kg and 2.5 kg respectively are on a horizontal surface and in contact with a circular vertical wall. The vertical wall makes a circle of radius 1.25 meters. Both of blocks are always, let me say, in contact with each other as shown in the top view. The horizontal surface has negligible friction, whereas the coefficient of kinetic friction between the vertical wall and the blocks is 0.2. Now I have reached this point. Let me explain what's happening here. This is a top view as if you're standing above the table. This is a table, and that's the table. The table is horizontal. Here we're having a top view. Then we have two blocks that are in contact. They are placed on the table. There is no friction between the blocks and the table, so here we have no friction. And the blocks will move along a circle while remaining in contact with each other and remaining in contact with the inner walls. However, between the blocks and the inner wall there is friction, and we're talking about kinetic friction because there will be a relative motion between the blocks A and B together and the inner circle. You can imagine this inner circle to be a cylinder. A force of constant magnitude F is being exerted on block A such that the blocks move around the circular wall. The direction of the force is constantly changing such that it is directed tangent to the circular wall. Now suppose if the blocks are here, then the force F would be up like that, such that it's always tangent to the circular wall. If the blocks moves at a constant speed and it takes them 10 seconds to go around the circle, the magnitude of F is most nearly. Then we need to determine the magnitude of the force F which causing the blocks to move at a constant speed. Although we have a force F, but why they are moving at a constant speed? Because it will be balanced by the kinetic friction. Then in order to determine F, we need to utilize the forces acting on the blocks. Now what are the forces acting on the blocks? Let me first consider the side view, which is easier. Now we have the pull of gravity down of the system combined. We have the normal push exerted by the table on the blocks, which is up. We have the pushing force, which is pushing them toward the right. And we have the friction, which is opposing the motion toward the left. Now this is not enough. Also we need to consider the top view in order to utilize any additional forces acting on the system. Let me say this is Fn1. There will be another force Fn2 exerted by the wall of the circular cylinder toward the center like that. Now in total, how many forces would be acting on the blocks? We have 1, 2, 3, 4 and 5. Now we're ready to utilize Newton's second law, so we can say that F naught is ma, and m in this case would represent the masses of the blocks A and B combined. Now we have the pull of gravity, we have the normal push Fn1, we have the normal push Fn2, we have the friction, and we have the pushing force, which is the capital F, and that would be equal to ma. Now in order to determine this force, we need to consider the tangential direction. I will name this direction to be, in this case, the horizontal, but remember this is the tangential direction, so let me write it to be the tangential. The pull of gravity would be 0, the normal push Fn1 would be 0, Fn2 would be 0, we have the friction opposing the motion, that would be minus Ff, now plus the pushing force, and that would be equal to 0 because we have no acceleration. Then basically the pushing force F would be equal to the friction. And we know that in this case we can say that the friction is given by the coefficient of kinetic friction mu k multiplied by the normal push. And here comes the tricky part. Which normal push I'm gonna use, Fn1 or Fn2? Now remember that this Fn is related to the kinetic friction, and in this case we need to use Fn2 because it is the one which is related to the surface which is causing the friction, then that would be 2. Now what is the value of Fn2? It's the only force acting toward the center, and we can say that Fn2 would be mv square over r, and that would be mu k mv square over r. Mu k is given by 0.2. Now before I replace the value of mu k, let me do the following. We don't have the speed of the blocks along which they are traveling along the circle. Then we need to find the expression of the speed. We know that the speed is distance over time. Now we have the time, which is 10 seconds, but what about the distance? They are traveling along a circle, then the distance along the circle would be the circumference given by 2 pi r divided by t. And now let me replace these expressions. We have mu km divided by r. Now v square would be 4 pi square r square divided by t square. And this would cancel with that. Now mu k is given by 0.2. The mass is combined given by 3.5, which is 2.5 plus 1. The speed, now we're looking at this expression. We have 4 pi square. The radius is given by 1.25 divided by the time, which is 10 to the power 2. Plugging that expression on the calculator, you're gonna find that the pushing force is given by 0.35 newtons. Now exercise 5, a block of mass m is placed against the inner wall of a hollow cylinder of radius r that rotates about a vertical axis with constant angular velocity omega as shown above. In order for friction to prevent the mass from sliding down the wall, the coefficient of static friction mu between the mass and the wall must satisfy which of the following inequalities? Now here we're talking about the edge of motion, and this is obvious from the text because we're talking about the friction to prevent the mass from sliding down. Then we're at the edge of motion, then friction can be directly used to be mu s Fn. And in order to determine the expression of the static friction, we need to utilize the forces that are acting on the block. We have the pull of gravity down. Now remember that the friction in this case, it will be up. Why? Because it happens to be between the surface of the inner cylinder, and because the tendency of motion is down, then the friction would be up, and we have the normal force toward the center. And now we can say that F net is ma. Now what are the different forces acting on the block? We have the pull of gravity, we have the normal push, we have friction, and that would be equal to ma. Now let's utilize different directions. Let me first consider the centripetal direction, and that would be 0 plus 0, sorry, the normal push is Fn, plus 0 equals to mv square over r, because if we're considering A to be the centripetal direction, that would be mv square over r. Then Fn is given by mv square over r. Now along the vertical, that would be the pull of gravity, mg, balanced by the friction, which is given by mu s Fn. And we know that in this case, mu s Fn would be given by mv square over r. M with M would cancel, then G would be given by mu s V square divided by R. Then mu s would be given by Rg divided by V square, but we need to talk about the inequality. Since we need a minimum value in order for that to happen, then we're talking about the minimum value given by Rg divided by V square. Then mu s would be greater or equal to Rg divided by v square, and the correct expression would be none of these because v should be replaced by omega r. So rg divided by v square, that would be rg divided by omega r to the power of 2, and that would be g divided by omega square multiplied by r, which makes b to be the correct choice. And finally, exercise 6, which is an exit ticket for today's video. A sphere of mass m is connected to a lightweight rod of length L and moves at a constant speed greater than radical Lg in a vertical circle as shown. The magnitude of the forces the rod exerts on the sphere at positions A, B, and C are given by Fa, Fb, and Fc respectively. Which of the following expressions is equal to 2mg? Then which of the following linear combinations of A, B, and C respectively gives us 2mg? Then we need to utilize the different forces acting at the points A, B, and C and determine the expression of each. This can be done by using Newton's second law. At point A, we have the pull of gravity down, and we have the force exerted by the rod on the sphere M, and you can understand that as or similar to the tension force, then that would be Fa. Now at the point B, that would be the pull of gravity down, and the force, why it will be pointing toward the center, because it's similar to the pull of gravity to the tension force. And at the point C, we have the pull of gravity down, and we have Fc toward the center. Now in this case, we can say that Fa plus Fg would be equal to mv square over r, which means that the force at the point A would be given by mv square over r minus mg, and Fb would be simply equal to mv square over r. And for the point C, we have that Fc, which is the positive direction along the center, minus mg equals to mv square over r. Then Fc would be given by mv square over r plus mg. Then Fc would be given by mv square over r plus mg. And if you try all of these combinations, Fc minus Fa would be mv square over r plus mg minus mv square over r minus mg. This would cancel. Mg minus mg would add up to 2mg, and the correct expression would be E. Then that's it for me in this video, guys. See you soon in a new one.